All right, let's review these last few learning targets in Unit 6. So this one is, I can identify properties of acids and bases and compare and contrast the different theories about acids and bases. Okay, so let's add 2 properties into each of the sections and some that overlap. So properties of both acids and bases. They are both corrosive. They also both add ions to solution. They're different ions, but properties of acids, they taste sour. They turn universal indicator red. pH 0 to 7. They add hydrogen ions to solution. Bases taste bitter. Bases turn universal indicator blue. Indicator blue. They have a pH 7 to 14, and they add hydroxide ions to solution. So I added a few extra there. Identify each of the following as an acid or a base based on the formula. So this first one must be one of the Bronsted-Lowry bases. It doesn't have an OH in the formula, but it can accept a hydrogen from H2O and leave behind a hydroxide ion. And then that would become NH4. That's ammonia. Letter B, this is an acid. Acids typically start with an H. That one is actually sulfuric acid. And then this one is an Arrhenius base because it has OH in the formula. And then the last one is another acid. Starts with an H. According to Bronsted-Lowry theory, bases are substances that can accept a proton from water and leave behind OH minus. Write a Bronsted-Lowry equation showing how the hypochlorite ion, which is the main ingredient in bleach, interacts with water. So it's going to steal the H and become HOCl, and then it's going to leave behind this hydroxide ion and make this a basic solution. Next learning target, I can explain how the concentrations of solutions relate mathematically to their pH value. I can explain why strong acids have a low pH and why strong bases have a high pH. So for this one, we've got scientific notation. This would be 1 times 10 to the negative 4th, which means it's a pH of 4 and it's an acid. This next one, if I write it out, it's 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros. And it would have a pH of 10. That is basic. And neutral would have a pH of 7. 1 times 10 to the minus 7th molar. Add my units for these. And this would be 0.00000001 molar. Which has a higher pH? A 1 molar solution of NaOH, strong base, or a 1 molar solution of NH3, a weak base? The higher pH would be the strong base because it completely dissociates in solution. And so it's going to have more hydroxide ions than this one, NH3, a weak base. It will grab some hydrogens from water, but it also will just stay NH3 as well. So it's a weak base. It doesn't put as many hydroxide ions into solution. So the more hydroxide ions there are, the higher the pH is, the closer to 14. All right, which will have a higher pH? A strong acid or a weak acid? Same concentration. Oops, this should be HF. So this one would be the HF would have a higher pH because if it's a really strong acid, it's going to completely dissociate. And so it's going to have more hydrogen ions in solution, and that makes it have a lower pH. So the answer would be the weak acid has a higher pH because it doesn't fully dissociate. A lot of the HFs still stay together and only some break up. So you don't have as many hydrogen ions in solution. Okay, last learning target, I can predict the products of a neutralization reaction. I can calculate the concentration of a mystery acid or base given data from a titration experiment. So we know always that we make water, and then what else is left over? Aluminum's got a +3 charge. Nitrate has a -1 charge, so this will form AlNO3-3. And then this is not balanced. We need a 3 in front of the NO3-3. That's 6 H's, and we need a 3 here. Identify the acid, the base, the salt, and water. Okay, let's do another one. We know we're going to make water because we're adding an acid to a base. And then let's see what else is left over. Na has a +1 charge. CO3 has a -2 charge. So this is Na2CO3, which means we need a couple of 2's to balance. And of course, let's also label our water and our salt. All right, last question. Use the neutralization reaction below to solve the following calculation. Okay, and I'm going to copy and paste this again just so I can write underneath it what we've got. I'm going to divide my milliliters by 1,000 to change that into liters. And let's write underneath each what we've got. So we've got 0.15 liters of NaOH, and the concentration is 0.5. And it's neutralizing 0.25 liters of my unknown acid. So first step, multiply liters by molarity to figure out how many moles I needed to add of the base. 0.15 times 0.5. We needed to add 0.075 moles of NaOH. Now, for every 2 moles of NaOH, this is from the balanced equation, you only need 1 mole of H2SO4 to neutralize. So 0.075 divided by 2, 0.0375 moles of H2SO4 were neutralized, divided by how many or how much there was in volume, divided by 0.25. So the concentration would be 0.15 molar H2SO4. Boom. And that is it. That's what you need to know for these 3 learning targets.